All right, everybody, moving right along here to chapter number 6. Chapter number 6 is on something called the mole, and it's actually a unit of measurement that I talked very briefly at the very beginning of the year when we were first talking about some of our units of measurement, some common units of measurement. We're going to get into it right here with chapter 6, as well as chapter number 8, because chapter number 8 is kind of almost like a combined chapter with 6 here. So 6 and 8 are very heavily intertwined with each other, and they're all centered around this concept called the mole. Now, before we really get into the mole and what it means, there's going to be a couple of bits of little review here that I do want to allocate some time to with this first lecture video for chapter number 6. Okay, and it has a lot to do with measurements in general and this concept of dimensional analysis. Okay, so if we remember, and hopefully we do, all measurements contain two things specifically, right? It is a number plus a unit, right? So every measurement is a number plus a unit, right? So for example, we've got some measurements right here. Okay, 12 people, 14.0 grams, and 1.25 mol, which is just basically moles, right? All these are measurements, right? They contain a number and a unit, right? 12 being the number and people being the unit, right? 14.0 being the number, grams being the unit, 1.25 being the number, and moles being the unit, right? So these are all units of measurements here. Now, with that comes the idea, once again, of significant figures, all right? Measurements are expressed to a certain number of significant figures, right? So anytime you are dealing with measurements, guys, you have to be always thinking significant figures. And this is where a bulk of this review I was just referencing is going to kind of come from, right? This idea of sig figs, okay? Now, this other idea up here at the top here, dimensional analysis, can be used to convert between different units, right? And this is a lot easier than it might sound, okay? But before we actually get into doing those unit conversions between our different types of units, right, let's do a quick little basic review of the rules for sig figs, okay? Here's the PLAR method if we remember this one, right? So PR meaning present left. If a decimal point is present in the number, start counting on the left-hand side with the first non-zero digit and then keep counting every digit until the end. Present left, PL. And then there, of course, there's the absent right, the AR, which is the right-hand side. If a decimal point is absent right, start counting on the right-hand side with the first non-zero digit and then keep counting until the end. So from the right going to the left is AR. From the left going to the right is PL, PLAR. Okay. Of course, our sig fig rules for our four different mathematical operations, right? When it comes to adding or subtracting different measurements, making sure that we are rounding based on the number of decimal places in all of our numbers, right? Meaning the fewest number of decimal places. So adding or subtracting, fewest number of decimal places. Okay. When it comes to multiplying or dividing numbers, right, we're going to make sure we round to the lowest number of significant figures, right? So if there's a set of 3 numbers being multiplied and 2 of them have 4 sig figs and 1 of them have 3 sig figs, the lowest number of sig figs is 3. So making sure our number, our final answer, our product becomes an answer with only 3 sig figs. Okay, lowest number of sig figs for multiplying, dividing, adding, subtracting is lowest number of decimal places. Okay. Now, this idea of dimensional analysis, and we're going to do a couple examples of this in class when I see you guys next. So here are going to be a couple of the rules. There's 5 total rules to kind of associate with dimensional analysis. This first one here is going to be a really important one. Circle what you are given, put a box around what you are looking for. Now, why is this important? Why is it important to be able to circle what you are given and put a box around what you're looking for? It's going to help isolate some of the main sort of portions of a question to, essentially give you a better opportunity and a better chance to answer the question without all the extras that are being present, right? And we can think of this idea of circling what you're given and putting a box around what you're looking for due to the nature of the fact that a lot of these dimensional analysis-based questions, when we're converting from one unit of measurement to another unit of measurement, come from the fact that a lot of these are going to be word problems, right? So you might have a situation where you've got, 3 sentences, 2 or 3 sentences worth of words here. That could be anywhere between 15 to 25 different words, right? With some measurements associated with those words. And it's going to be really important to be able to isolate and break down those 20 to 30, sometimes more words, 2 or 3 sentences, breaking those 2 or 3 sentences down into just a couple of main things we're looking for, right? So if you are given measurements and we being able to identify what we're looking for by putting a box around it, it's going to put us above the competition, give us a little bit of a leg up there. So it's, less things in the way, right? Number 2, write a unit equality. A unit equality is where you set 2 different measurements equal to each other, right? So a very basic one will be to say, well, how many different, how many feet are there in, or I'm saying this incorrectly, how many inches are in 1 foot, right? If you were to try and determine that, of course, we all hopefully know that there are 12 inches in 1 foot. Well, if I have 12 inches, 12 inches is the same as 1 foot, okay? So this is a unit equality. It's taking 2 different units of measurement, inches and feet, and setting them equal to each other with different numbers, right? We clearly have a different number here, 12, and that number is very different from number 1. If I were to take my eraser here and erase the inches and the feet here, would this still make sense? Does 12 equal 1? Absolutely not, right? 12 definitely does not equal 1. But the reason why we were able to set 12 equal to 1 is because of these units here, these units of measurement, inches and feet, okay? So because of this, we have 12 inches equaling 1 foot. This whole thing right here, I'm going to get rid of these arrows here as well, okay? This whole thing I'm circling right here is what's known as a unit equality. It's when you are setting 2 different units equal to each other, okay? Unit equality, right? We have to get good at actually creating these unit equalities and setting them equal to each other, because it's going to help pay dividends in the future when it comes to writing that unit equality as 2 conversion factors. Now, what the heck is a conversion factor, okay? If I take this same unit equality here of, let's say, what was it, 12 inches equals 1 foot, okay? Well, how do I take this one unit equality and create 2 conversion factors out of it, okay? Essentially, guys, you're taking each of these measurements here, this 12 inches and this 1 foot here, and we're creating fractions with them, right? That's it. We're creating a fraction with both of them. Now, how does that work and what does that literally mean? Well, what I quite literally mean is we're going to make a fraction of this. So if I take this one measurement here of 12 inches and make a fraction with it, using my 1 foot, well, I do 12 inches divided by 1 foot. Now, that is one of my 2 conversion factors. So that's how you make a conversion factor to start. Okay, you take the measurements from this unit equality, the 12 inches and the 1 foot, and you literally create a fraction of them. Put one in the numerator, one in the denominator. Right, that's one of your 2 conversion factors. Now, how do I get my second conversion factor? Well, you literally just flip them. Okay, you have them change places. So whatever's in your numerator here, the 12 inches, should now be in your denominator, and whatever's in your denominator should now be in your numerator, right? So now instead of having 12 inches in the numerator, we're gonna have 1 foot in the numerator, and instead of having 1 foot in the denominator, we're gonna have 12 inches in the denominator, okay? So now we have our 2 different conversion factors. Okay, and again, we're going to do a couple examples of this in class to make this kind of much easier on us in the future, okay? But that is our 2 conversion factors. Now, number 4 asks us to set the problem up so that the units cancel. Okay, I'm not going to really go too much detail into this one and save that for the examples we do in class, but it will make sense in terms of why we needed to actually, create these 2 conversion factors and which one we should pick between the 2 we created, right? So that our units do in fact cancel. And then lastly, put a box around your final answer. That's just to kind of make it nice, clean, and concise, so you can show the reader, aka me, that the final answer is exactly what you're putting a box around. Okay. Now on to this last concept that we're going to touch on before we close up this video here, the mole. Okay. Well, plain and simple, guys, the mole is an SI-based unit used to measure the quantity of matter. Okay, it's a totally wildly different concept than we're used to seeing. It's not one we've really talked too much about. I know I mentioned the mole at the very beginning of the school year, but it's coming now right here in chapter 6. Now, we can think about donuts, right? Everyone here loves donuts, or hopefully to a degree likes some donuts, right? So now let's go through each of these. Think of all of these guys here as a couple of different unit equalities. And again, unit equalities are when you're setting 2 different measurements equal to each other, right? So, for example, If you have 1 dozen donuts, that's the same thing as saying, well, I've got 12 donuts, okay? Somebody with 12 donuts and somebody with 1 dozen donuts, exact same number of donuts, right? 1 dozen equals 12 total donuts here, okay? Now, what if we take 1 dozen candy bars and set that equal to 12 candy bars, right? Same thing, right? Using this word dozen holds a value to us, right? So if I say the word dozen, the number that instantly comes to your guys' mind should be the number 12. If I say the word couple, that number that instantly comes to your mind is going to be the number 2, right? If I say I have a couple of donuts or I have a couple of candy bars, generally speaking, most of us are going to be thinking the number 2. If I say I have a few donuts or a few candy bars, generally speaking, the word few is in the implication we're talking about 3 for the most part, right? Now, if I have 1 dozen atoms, I still have 12 atoms. Again, this word dozen holds a numerical value to us, right? Just by saying that word dozen, that tells us we're dealing with 12 of whatever it is we're applying it to. Okay, dozen atoms, 12. Dozen candy bars, 12 dozen candy bars. Okay, or 12 candy bars. Dozen donuts, 12 donuts. If I have a dozen molecules, it's still 12 molecules. But what if I have 1 mole of donuts? Well, just like that word dozen holds a value of 12, this word mole holds a value of what we've got right here, which is this number, 6.02 times 10 raised to the 23rd power. I get that that's a totally kind of wildly different comparison between 12 and this massive number of 6.02 times 10 to the 23rd. Okay, that's very, very different, right? But it's a number we're going to get used to seeing a lot between now and the end of this chapter, as well as going into chapter 8. But let's see it again in the form of another unit equality. If I have 1 mole of candy bars, it's still the same number of candy bars. It's just talking about candy bars instead of donuts. 6.02 times 10 to the 23rd candy bars. If I have 1 mole of atoms, it's still the same number of atoms. 6.02 times 10 to the 23rd atoms, right? Just by saying that word mole, it is the implication that the number we're referring to is 6.02 times 10 to the 23rd. And if I have 1 mole of molecules, it's the same thing, the same number, 6.02 times 10 to the 23rd molecules here. Okay, I get it. It's kind of a wacky concept to think about, but it's one we'll talk more about in class when I see you. Okay. Now, with this idea of the mole and converting between moles and particles, it's going to be based on this conversion factor here, or this unit equality here, right? So if I have 1 mole of something, I have 6.02 times 10 to the 23rd particles of it, right? Obviously, like I mentioned before, guys, if I had, 1 set equal to, and I'm going to try my best to get rid of this word here, mole, okay? Obviously, if I have these 2 numbers here, right, one is not the same, right? 1 is very much different than the number 6.02 times 10 to the 23rd, right? 1 does certainly not equal 6.02 times 10 to the 23rd, okay? Those are 2 totally different numbers. They're not equal to each other, all right? But the way that we get them equal to each other is by having the word mole and the word particles in this unit equality, right? Now, this word particles can kind of be interchanged between multiple different ones, right? If I had the word atoms here, or molecules, or ions, or particles, right? These 4 words, particles, atoms, molecules, ions, okay, are pretty interchangeable with each other, right? So if I had 6.02 times 10 to the 23rd atoms, or 6.02 times 10 to the 23rd particles, or 6.02 times 10 to the 23rd ions, right? Those are all the same thing and mean the same thing. They're very interchangeable with each other, particles, atoms, molecules, ions. Okay. Now, what are the 2 possible conversion factors here, right? Again, a conversion factor is when you take the 2 measurements from your unit equation, okay, your unit equality, and kind of create fractions out of them, right? So if I were to create a fraction with the unit, a measurement rather, 1.000 mole, and the measurement 6.02 times 10 to the 23rd particles, right? These are 2 measurements here. If I were to create a fraction with them, one of them is going to look like this. Okay, I take my 6.02 times 10 to the 23rd particles and put that in the numerator of my fraction, and then the other measurement goes in the denominator, my 1.000 moles. That's my 1 of 2 conversion factors. Now, all I have to do to create my second conversion factor is swap them, okay? Put what's in the denominator in the numerator, and what's in the numerator in the denominator, and you are given this. 1 mole now in the numerator, and 6.02 times 10 to the 23rd particles in the denominator. And guys, when I see you in class next, I'll show you exactly what you're supposed to do with these two conversion factors. Okay, see you in class.